Alright, so this is lesson number 3 of module 12 on IPv6. Earlier in this module, you learned that there are three broad categories of IPv6 addresses. That's unicast, anycast, and multicast. Now this topic goes into more detail about multicast addresses. With IPv6 multicast addresses, they're similar to IPv4 multicast addresses. Now recall that a multicast address is used to send a single packet to one or more destinations, multicast group. IPv6 multicast addresses have the prefix FF00:8. So you can tell that it's a multicast IPv6 multicast address when you are able to see the FF00:8. That should indicate to you that there is a multicast address. Now do note that multicast addresses can only be destination addresses and not source addresses. Okay, and there are two types of IPv6 multicast addresses that we will see in the next set of slides. We have well-known multicast addresses and solicited node multicast addresses. Okay, so well-known multicast addresses, these are already a set range of addresses that are well known. Solicited node, the word solicited is more or less a query. Okay, query node addresses, okay, which we will look at. Okay, so let's take a look at first of all well-known IPv6 multicast addresses. Now for well-known IPv6 multicast addresses, they are assigned. Okay, assigned multicast addresses are reserved multicast addresses specifically for a predefined groups of devices. Now an assigned multicast address is a single address used to reach a group of devices. Remember, this is one-to-many. Okay, so single address that can be assigned to use to reach a group of devices. Okay, now you recall in the previous slides that multicast addresses can only be destination addresses, okay, not source addresses. So that means that in this slide where we come across the point that an assigned multicast address is a single address used to reach a group of devices running a common protocol or service, that means that that address is assigned to this group of devices. So a node may want to reach all of those devices, and how it will be able to do that is to use that single multicast address to be able to reach a group of devices running that particular common protocol or service. So assigned multicast addresses are used in context with specific protocols such as, example, DHCP version 6. So these are the two common IPv6 assigned multicast groups. You have the FF02:1, which is the all nodes multicast group, and then this is a multicast group that all IPv6 enabled devices join. Now a packet sent to this group is received and processed by all IPv6 interfaces on the link or network, and this has the same effect as a broadcast address we find in IPv4. Okay, with the FF022, this is all routers multicast group. Okay, all routers multicast group. Now as the name implies, it's a multicast group that all IPv6 routers join. So a router becomes a member of this group when it is enabled as an IPv6 router. Remember with that command IPv6 unicast routing. Once that is entered in the global config command, that router automatically becomes a part of the all routers multicast group. And if one single node were to send the device to all IPv6 enabled routers, it will use this FF022. Okay, that's the all routers multicast group. Now FF021, remember that this is all nodes. Every IPv6 enabled device joins that all nodes multicast group, and it's pretty much straightforward because you see here all nodes. So it's like a broadcast to all the devices, all IPv6 enabled devices. What about the solicited, okay, solicited nodes. With solicited node IPv6 multicast address, it is similar to the all nodes multicast address. Now, the advantage of a solicited node multicast address is that it is mapped to a special Ethernet multicast address. Now, this allows the Ethernet network interface card to filter the frame by examining the destination MAC address without sending it to the IPv6 process to see if the device is the intended target of the IPv6 group. Okay, so it's very much like the broadcast address in IPv4 or the all nodes multicast address in IPv6. Okay, so do note here that the main advantage or the key advantage of this type of multicast address is it's mapped to a special Ethernet multicast address. Okay, so this special Ethernet multicast address allows the network interface cards to filter the frames by examining the destination MAC address, even without sending it to the IPv6 process. Okay, so two important multicast addresses we've discussed. Okay, we have the solicited node IPv6 multicast address, and we also have the well-known IPv6 multicast address. Okay, so in the well-known multicast IPv6 multicast address, we have the FF021, which is all nodes, and we have the FF022, which is all routers multicast group. And with the solicited node, this is similar to the all nodes multicast IPv6. Okay, so let's have a look at the second concept of this lesson, which is on subnetting an IPv6 network. Now again, you don't necessarily need to subnet an IPv6 network. However, subnetting is very important because we want to segment the network into smaller domains. Okay, that's the whole idea why we want to subnet. Okay, so we want to reduce the size of the broadcast domain. That's why we create smaller segments or smaller subnets. Okay, so even though IPv6 there's a huge number of addresses available, the necessity to subnet comes from the fact that we want smaller broadcast domains. That is why we create subnets. So we use a large address range, but we can segment it into smaller broadcast domains. So the introduction to Module 12 mentioned subnetting an IPv6 network. And it also said that you might discover that this is a bit easier than subnetting an IPv4 network. Well, this part of the lesson 3 is going to be very short. We don't need to do any complex calculations for subnetting like we did in IPv4. All we need to know is to see what part of that prefix address do we use to subnet, and it's just a matter of arranging the bits that will help us to identify. Okay, so you recall that with IPv4 we had to borrow bits from the host portion. You remember that you had to divide an IPv4 address into two parts. You had the network portion and then you had the host portion. Okay, so you recall that we had to borrow bits from the host portion, from this part, to create subnets. And to add additional host, we had to borrow bits from this part of the network, this part of the address, if we wanted to create or add additional number of hosts. And this is because subnetting was an afterthought with IPv4. With IPv6, it was designed with subnetting in mind. Okay, so a separate subnet ID field is already created in the IPv6 global unicast address, and that's basically the main thing that we need to pick up in this part of the module. That there's nothing complex about subnetting in IPv6 except that you need to know that you are given 16 bits for your subnet ID, and all you're doing here is you're just playing around with that 16 bits to create segments or create subnets. So that's the main idea here. Okay, the subnet ID field is what we are interested in. So we have the we usually draw our line here, and we say that this is the first 64 bits, this is the last 64 bits, and we know that this is the interface ID, and we know that this is the prefix. Okay, so the prefix is further divided up into two parts again. Okay, so you have the global routing prefix. Usually this is the GUA, global unicast address. Remember that it's a routable address. Okay, so with the global unicast address, the global routing prefix is 48 bits, and it's usually that global routing prefix is usually given by either a method such as select or DHCP version 6. And what we are interested in if we are going to create subnets is the subnet ID. So subnet ID is just 16 bits only, and it's in between global routing prefix and the interface ID. So a benefit of a 128-bit address, as I've mentioned earlier, is that its ability to support more than enough subnets and hosts per subnet for each network. Okay, because of the large address space available. So even with a 16-bit subnet ID, if you do a 2 raised to the power 16, that's quite a lot. Okay, it creates up to 65,536 subnets. Okay, if you do 2 raised to the power 16. Now 64-bit interface ID, that's this one. Okay, since this is our network portion, to find the number of networks, 2 raised to the power 16, and we end up with 65,536 subnets. Now to find the number of hosts, 2 raised to the power 64, because you have a total of 64 bits on this part. Okay, that will give you the number of hosts, just like what we normally did with IPv4. And with a 64-bit interface ID, that supports up to 18 quintillion host IPv6 addresses. Okay, that's about 3, 6, 9, 12, more than 16 zeros. Yeah, more than 16 zeros. So subnetting into the 64-bit interface ID or host portion, it's possible. Okay, we can of course borrow up to this part if we wanted to increase the number of subnets, but it's not really necessary, and it's rarely required. Okay, so that should tell you that in terms of IPv6, so that should give you an idea that in terms of IPv6 subnetting, it's not only easy to work out the subnets, but it's also easier to implement than IPv4, because there is no conversion to binary required. To determine the next available subnet, you just count up in hexadecimal to find the next available subnet. So we'll see an example in the next slide. Okay, so assume an organization has been assigned the 2001. Again, this is a global unicast. 2001 DB8 ACAD double colon, and then you have the rest is all zeros. The double colon, that's rest is all zeros, /48. It has a global routing prefix with a 16-bit subnet ID. Okay, 16-bit subnet ID. Okay, so 16-bit subnet ID should give us an indication how many bits we have to work out the number of hosts, and how many bits we have to work out the number of subnets. So if we just take a quick peek back at the previous slide, remember we have 16 bits that's predefined for subnetting. Okay, so when we come back here to this scenario, we have a routing prefix with a 16-bit subnet ID. So what does this mean? We go back to this picture here, this image here, and out of the total 64 bits, you take out 16 bits. Okay, you take out 16 bits. Why do we take out the 16 bits? That 16 bits is for subnet ID. Okay, so what happened to the rest? What about the rest now? Well, out of that 64 minus 16 for the interface ID, the rest all now becomes part of that 16 bits to work out the subnets. So how many is left then? Okay, how many is left then? 64 take away 16, how many is left? You worked it out? Okay. Okay, so we should know how many bits are available here. Added to this, that should give us the total number of bits that are available for us to find the subnet ID. Okay, so let's come back to this diagram here. When you add the numbers here, when you look at the 16 bits available, that will allow up to 65,000 subnets /64. So the global routing prefix in this case here is the same for all the subnets. Only the subnet ID hexstat is incremented in hexadecimal for each individual subnet. So have a look at this diagram here. You see we start off with ACAT 0000, and then we go 0001, 2, 3, 4, and it goes on and on until we get to the part where all the hexadecimal values have to go F, 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 F. Okay, that's the last. And we stop there. Okay, so we can't possibly write all of that here. There's not enough space to list 65,000 subnets, but you get the idea. All we are doing here is we're just incrementing from 0, starting 0 network, 1, 2, 3. So that's the, if we start, say, 0 network, okay? So 0, okay, 0, 0, 0, 0, okay? Double colon. The first host will be 1. Second host will be 2, 3, 4, 5, 6, and so on. Okay. For the next network, it will start with 0, 0, 0, 1. Double colon. First host will be 1, and then 2, and then 3, and it goes on and on. So you see, each of these is a separate subnet. So we have a total of 65,000 subnets. And then you can work out how many hosts will be in each of these subnets, given that you have a 16-bit subnet ID, okay, in addition to that other bits available, but 16 bits is for the subnet ID. So again, you can have 65,000 hosts. Oh, no, hold on. 16-bit subnet ID. 16-bit subnet ID, I think I made a mistake here. 16-bit subnet ID, not host ID. Okay, I was looking at the wrong thing. So that's the same 16-bit subnet ID. So you have the 64 bits. Okay, so again, you have a huge number of hosts in each of these subnets. So what this means is each subnet will have about, because you have 64 bits. So 2 raised to the power 64, again 18 quintillion you're looking at in each of these subnets. So that's quite a lot. So in most cases, it's rare for you to use up all of those hosts, okay? All of those host addresses within IPv6. But that's the idea here. That's basically how we subnet. We just increment each of those subnet hexstat by adding 1, 2, 3, 4, and so on. Okay, here's another example with over 65,536 subnets to choose from. The task for you as a network administrator becomes one of designing a local scheme to address the network. And one of the best practices when you're designing networks is to scale, okay? Be able to design with scalability in mind, envisioning the network to change and grow over the years. So as shown in the figure here, the example topology you see requires 5 subnets, one for each VLAN, as well as for the serial link between R1 and R2. So that's one subnet, that's one subnet, that's one subnet, that's another one, that's another one, this is another one. Okay. So unlike the example for IPv4, with IPv6, the serial link subnet will have the same prefix length as the LANs. Okay. So it's not like we only need 2 and we need to fed a subnet. Now, although this may seem like we're wasting addresses, address conservation is not a concern when it comes to IPv6. Remember, that whole lot of addresses in just one single subnet alone is just too much. So that's fine. Okay. This is not a concern where we use only 2 and we waste the rest of it. Okay, because for IPv4, IPv4 was address depletion was a major concern. So subnetting, network address translation, that was used. VLSM was used to try and conserve. With IPv6, given the huge number of addresses available, wasting of addresses or address conservation here is really not a concern in terms of the use of IPv6. So you can see here that 5 subnets are now allocated each subnet. Okay, that's from the previous activity. So we can say that's for subnet 1, subnet 2, subnet 3, 4, 5. Okay, so we have 1, 2, 3, 4, and 5 here. Okay, so we can start assigning in that manner. Now, notice that's how easy it is when it comes to subnetting in IPv6. Okay, there's not really much involved. As long as you know that there's a 16 bits have been predefined or allocated in between the GUA, the global prefix, as well as the host ID or network ID, that should give an indication how many bits you're working with, and it's just a matter of knowing that you start from 0 and then 1 and 2 and 3 and onwards. So similar to configuring IPv4, the example here shows that each of the router interfaces has been configured to be on a different IPv6 subnet. So notice interface G00, let me change this, G00, notice it's 1:1, and then another interface is 2:1, another interface is 3:1. That's in reference to the previous slide. Okay, remember we have this 1, 2, 3, 4, 5, and so on. Okay, that concept is now applied here. So just like how we would assign each interface of a router to that particular subnet of the IPv4 address we've agreed to, it's the same applies to IPv6 as well. Okay, so that's basically it for lesson number 3. Like I said, IPv6 subnetting is not very complicated. Not much calculation is involved. Just a matter of identifying what address you are using and knowing that 16-bit has been given for you to use as the subnet ID, and you increment from there. That's on subnetting IPv6. On multicast addresses, remember there are 2 major types: well-known IPv6 multicast and solicited node IPv6 multicast. And usually with the all nodes multicast group, that's the same as the IPv4 broadcast. And then all routers, by default, every IPv6 enabled router is a part of the all routers multicast group. Okay, so that brings me to the end of lesson 3. By the time you complete lesson 3 module 12, you should now move on to transport layer. You skip module 13 ICMP, we will cover that during our bootcamp. These are just basic concepts we will cover. So go straight to chapter or module 14 on transport layer, Monday and onwards.